In April 2025, a team of astronomers pointed the James Webb Space Telescope at a faint, unremarkable-looking smudge of light they'd flagged in older survey data, hoping it might turn out to be something interesting. What came back didn't just turn out to be interesting. It became, officially, the single most distant galaxy human beings have ever confirmed. Light that left its source just 280 million years after the Big Bang, arriving at Webb's mirror after a journey so long that the universe itself has expanded to more than 50 times its size in the time that light spent traveling. And the astronomer who led the discovery didn't respond to what he found with simple excitement. He responded on the record by saying, "It looks nothing like what anyone predicted." Everybody, this is the real story of MOMZ-14, the current record holder for the most distant, earliest galaxy ever confirmed in the history of astronomy. And it's exactly the kind of discovery that earns a title like Scientists Rethinking Everything, because that's not an exaggeration here. That's a direct, published description from the research team itself. Let's start with what makes a discovery like this even measurable in the first place, because understanding the method is essential to understanding why this particular result carries so much weight. Astronomers determine how far away, and therefore how far back in time, a distant galaxy actually is using something called redshift. As the universe expands, the fabric of space itself keeps stretching, and light traveling through that expanding space gets stretched right along with it, shifted toward longer, redder wavelengths, the same basic principle behind the Doppler effect that makes a siren sound different as it moves away from you. The farther away an object is, and the longer its light has been traveling through an ever-expanding universe, the more extreme that redshift becomes. Astronomers assign these measurements a number, and higher redshift numbers correspond to greater distances and earlier points in cosmic history. Confirming a redshift precisely requires spectroscopy, breaking an object's light down into its individual component wavelengths, and looking for very specific, well-understood chemical signatures, emission lines produced by particular elements that let researchers calculate exactly how much that light has been stretched during its journey. It's worth understanding just how demanding that process actually is at the extremes Webb is now operating in. A redshift measurement isn't simply eyeballing how red an object looks in an image. Different chemical elements emit and absorb light at very precise, well-documented wavelengths when observed in a laboratory here on Earth, essentially a unique fingerprint for each element. When astronomers observe those same specific fingerprints in the light from a distant galaxy, but shifted to much longer wavelengths than they'd naturally appear, they can calculate exactly how much the universe's expansion has stretched that light during its journey, and from that, calculate precisely how long the light has been traveling, and therefore how far away and how far back in time the source actually sits. At a redshift as extreme as 14, 44, those chemical fingerprints have been stretched dramatically into the infrared portion of the spectrum, well beyond what visible light telescopes could ever hope to detect, which is exactly why a purpose-built infrared observatory like Webb was necessary to make a confirmation like this possible at all. This is where the story of MOMZ-14 actually begins. Rohan Naidu, an astrophysicist at the Massachusetts Institute of Technology's Kavli Institute for Astrophysics and Space Research, led a research team that had been combing carefully through existing James Webb imagery, searching specifically for candidate objects that might turn out to be extremely distant, extremely early galaxies once properly confirmed with spectroscopy. This search and confirm process is standard practice in this specific corner of astronomy, since imaging alone, even Webb's remarkably sensitive imaging, can only ever suggest that an object might be a legitimate high redshift candidate. A promising-looking smudge of light in a wide-field image could just as easily turn out to be a much closer, much less distant object that simply happens to appear reddish for entirely mundane reasons, dust obscuration, for instance, or an unusual stellar population. Only detailed spectroscopic follow-up can actually confirm a candidate's true distance beyond reasonable doubt, which is precisely the rigorous, methodical process Naidu's team applied here. After identifying MOMZ-14 as a genuinely promising candidate, the team turned Webb's instruments toward it directly in April 2025 to get a definitive spectroscopic reading. What came back confirmed a redshift of 14. 44, officially breaking the previous record held by a separate object called JWST Z14-0, which had been confirmed at a redshift of 14, 18 the year before. The team described the result in stark terms in their published paper, writing that MOMZ-14 represents the most distant spectroscopically confirmed source to date, extending the observational frontier to a mere 280 million years after the Big Bang. To put that timeline in perspective, the universe, as we currently understand it, is approximately 8 billion years old. Light reaching Webb's mirror from MOMZ-14 left its source when the universe was just 280 million years old, meaning we're looking at this galaxy as it existed when the entire universe was roughly 2% of its current age, If you scaled the universe's entire history down to a single calendar year, with the Big Bang happening at the stroke of midnight on January 1st, MOEMZ-14's light left its source sometime in the very first week of that year. An almost unimaginably early snapshot of cosmic history, arriving at our telescopes only now, over 5 billion years later. NIDA's own reaction to the discovery, quoted directly in a NASA statement released alongside the announcement, captures exactly why this find matters so much more than simply setting a new distance record. He said that with Webb, astronomers are now able to see farther than humans ever have before, and that what they're finding looks nothing like what anyone predicted, calling the result both challenging and exciting in the same breath. That's not the language of a researcher simply celebrating a new number in a record book. That's a scientist telling you directly that the object itself doesn't match the theoretical expectations his own field had built up over decades of modeling how the early universe should behave. If a real, currently unfolding scientific mystery like this, the kind actively forcing researchers to reconsider assumptions built up over decades, is exactly what you come here for. Subscribe now. Because the specific details of what makes MOEMZ-14 so strange go considerably deeper than just its extreme distance. Because here's where this story stops being simply about breaking a record and starts becoming genuinely destabilizing to existing theory. MOEMZ-14 is remarkably compact, measuring roughly 240 light-years across, which sounds small until you compare it directly to our own galaxy. The Milky Way spans roughly 100,000 light-years, meaning MOEMZ-14 is somewhere around 400 times smaller than our own galaxy in physical size. Despite that compact size, the galaxy contains roughly as much total mass as the Small Magellanic Cloud, a well-known dwarf galaxy currently orbiting our own Milky Way. And crucially, researchers caught this galaxy in the middle of an intense, rapid burst of star formation, meaning this tiny, distant object was actively and vigorously building new stars at the exact moment its light left for its 5 billion year journey toward Earth. Picture that scale comparison a different way. The Small Magellanic Cloud, the galaxy MOEMZ-14's mass roughly matches, took billions of years of cosmic history to reach that mass under normal circumstances, existing today as a fully mature, if modestly sized, satellite galaxy in our own cosmic backyard, studied extensively by astronomers for well over a century. MOEMZ-14 appears to have packed a comparable amount of mass into a structure hundreds of times smaller and physically denser, and did so within the first 280 million years of the universe's entire existence, a period so early that, under standard theoretical assumptions, galaxies were expected to still be relatively small, diffuse, loosely assembled collections of gas. And young stars, not compact, already massive systems midway through a vigorous starburst. Here's why that combination matters so much to cosmologists. Under the standard, long-established model of how the universe evolved after the Big Bang, galaxies are expected to form gradually, starting from small, diffuse clumps of gas that slowly collapse under gravity, merge with neighboring clumps over hundreds of millions of years, and only gradually build up the kind of mass, structure, and vigorous star formation astronomers associate with a genuinely mature galactic system. Finding a galaxy this compact, already this massive, and already this actively star-forming, at a point in cosmic history when the universe itself was barely 280 million years old, cuts directly against that gradual timeline. There simply shouldn't have been enough time, according to the standard model, for a system like this to have already assembled and begun forming stars this vigorously. This isn't actually a brand new problem MOEMZ-14 created entirely on its own. It's the latest and most extreme entry in a pattern that's been building steadily since Webb first began operating in 2022. The research team's own published paper addressed this directly, noting that since Webb began its science operations, the telescope has spotted more bright, ancient galaxies than scientists had expected to find at these extreme distances, and that this unexpected population has, in the team's own words, electrified the astronomical community while raising fundamental questions about how galaxy formation actually worked in the first 500 million years after the Big Bang. That's a direct acknowledgement, published in the peer-reviewed scientific literature, that an entire subfield of cosmology has a genuine, ongoing, unresolved problem on its hands. There's a second layer of strangeness buried in MOEMZ-14's chemistry that adds even more weight to the mystery. Researchers found that the galaxy is notably rich in nitrogen relative to carbon, a specific chemical ratio that closely resembles what astronomers observe in globular clusters. The ancient, extremely tightly bound clusters of thousands to millions of stars found throughout our own Milky Way today, thought to be among the oldest stellar structures anywhere in the nearby universe. Finding that same distinctive chemical signature in a galaxy dating back to just 280 million years after the Big Bang suggests that whatever process produces this specific nitrogen-rich chemistry in globular clusters might have already been operating in the very earliest generations of stars and galaxies the universe ever produced, far earlier than most existing models would have predicted that particular chemical pathway could even get started. That chemical detail carries real weight beyond simply being an interesting coincidence. Globular clusters in our own galaxy have puzzled astronomers for decades precisely because of this unusual nitrogen enrichment, a pattern that requires very specific, high-temperature nuclear fusion processes happening inside certain types of stars, processes that typically require multiple generations of earlier stars to have already lived, fused heavier elements, and died, seeding their surrounding environment with that enriched material before a new generation of nitrogen-rich stars could form from it. Finding a similar signature this early in cosmic history raises a genuinely uncomfortable question for existing theory. Either that nitrogen enrichment process can happen dramatically faster than previously assumed, compressing what was thought to require multiple generations of stellar life cycles into a window of just a few 100 million years, or astronomers are looking at evidence for an entirely different formation pathway for this specific chemical signature, one that doesn't require the same lengthy multi-generational process globular cluster formation was assumed to need. Neither option is a small incremental correction to existing theory. Both would represent a genuinely significant revision to how astronomers understand the chemical evolution of the earliest stellar populations the universe ever produced. This mystery didn't begin with Z14, and understanding its predecessor helps show just how quickly this entire field has been forced to revise its expectations. The previous record holder, JWST Z140, confirmed in 2024 as part of the JWST Advanced Deep Extragalactic Survey, generated its own wave of scientific reconsideration when a detailed 2025 follow-up study, published in the journal Nature Astronomy, revealed the galaxy was unexpectedly bright and chemically complex, containing significant amounts of oxygen, a heavier element that typically requires multiple earlier generations of stars living and dying to build up in meaningful quantities. That oxygen signature suggested the galaxy had already been actively forming stars for roughly 100 million years by the time its light left for Earth, implying that star formation in the early universe began even earlier than previously assumed, directly challenging existing models of how quickly the first galaxies could actually assemble and mature. Z14 didn't resolve that earlier controversy. It deepened it, pushing the observational frontier even further back, while displaying its own separate set of chemical and structural surprises that don't cleanly fit the models either. Taken together, these back-to-back record-breaking discoveries have created what one broader overview of Webb's recent findings described directly as a genuine crisis in early universe cosmology, one that ground-based telescopes, limited by Earth's atmosphere and far less sensitive infrared detection capability, could never have triggered on their own. It's worth being precise about what kind of crisis this actually is, because the word gets thrown around loosely in science journalism. This isn't a crisis threatening the fundamental validity of the Big Bang model itself. The overwhelming body of independent evidence supporting an expanding universe that began in a hot, dense state remains completely intact and unchallenged by any of this. What's genuinely being challenged is the far more specific, detailed model of exactly how quickly galaxies were able to assemble, grow massive, and begin vigorously forming stars in the first few 100 million years after that beginning. That's a real substantive scientific problem, but it's a problem about the details of galaxy formation timelines, not about whether the broader framework of modern cosmology is somehow fundamentally wrong. Astronomers currently have several competing explanations on the table for why the early universe keeps producing galaxies that appear far more massive and mature than expected this early in cosmic history, and none of them has yet emerged as a clear, universally accepted winner. One leading possibility is that star formation efficiency, the rate at which available gas actually converts into new stars, may simply have been considerably higher in the early universe than current models assume, allowing galaxies to build up mass and stellar populations faster than the standard theoretical framework predicts. This idea has gained some traction because the very early universe genuinely was a different environment in measurable ways, denser on average, with gas clouds that hadn't yet been shaped and disrupted by billions of years of stellar feedback, supernova explosions, and black hole activity the way gas in the present-day universe has been. It's plausible, under this theory, that conditions in that earlier environment simply allowed collapsing gas to convert into stars considerably more efficiently than anything astronomers observe happening in nearby present-day galaxies. Another possibility involves the initial mass function, the statistical distribution describing what mix of small and large stars typically forms out of a given cloud of collapsing gas, with some researchers proposing that the earliest generations of stars may have skewed toward more massive, more luminous stars than what forms in the universe today, making these early galaxies appear brighter and more developed than their actual total stellar mass would otherwise suggest. Under this explanation, part of what looks like an impossibly rapid mass buildup might actually be something closer to an optical illusion of sorts, not because the galaxies are somehow fake or misidentified, but because a population dominated by unusually large, unusually bright stars would naturally appear far more luminous and evolve for its actual total mass than an equivalent population built from a more typical present-day mix of star sizes. A smaller, more contrarian group of researchers has gone further, arguing that these repeated accumulating discrepancies might eventually require more fundamental adjustments to underlying cosmological parameters themselves, potentially including how astronomers calculate the age and expansion rate of the universe as a whole, though this remains very much a minority position within the broader field. And it's worth being direct that none of these competing explanations has achieved anything close to universal acceptance yet. This is a genuinely open, actively contested area of active research, not a settled debate quietly waiting for a final consensus. And it's entirely possible the eventual explanation turns out to be some combination of multiple factors working together, rather than any single theory cleanly winning out over the others. What makes this entire unfolding story particularly compelling from a viewer's standpoint is how transparent the researchers themselves have been about not having all the answers yet. This is refreshingly different from a lot of science reporting that tends to package uncertainty as false confidence. Naidu and his colleagues aren't claiming MOMSI 14 proves any single specific theory correct. They're documenting, carefully and rigorously, exactly what the data shows, and being explicit that it doesn't match their prior expectations, then leaving the harder work of explaining why to the wider scientific community's ongoing efforts. That's genuinely how healthy science operates, and it's worth appreciating that distinction, especially when a topic this compelling is prone to attracting either baseless hype or comparably baseless dismissal from various corners of the internet. There's also a broader technological story wrapped up inside this discovery that's easy to overlook amid the cosmological implications. The fact that Webb can detect and spectroscopically confirm objects this faint, this distant, and this ancient at all represents an extraordinary engineering achievement in its own right. Webb's instruments are specifically tuned to detect infrared light, precisely because light from these extremely distant, extremely redshifted early galaxies has been stretched so dramatically by the universe's expansion that it no longer falls within the visible spectrum human eyes, or even Hubble's primary instruments can effectively detect. Confirming a redshift as extreme as 1444 required not just capturing a faint smudge of light in an image, but breaking that faint light down into a detailed enough spectrum to definitively identify specific chemical emission lines and calculate their precise wavelength shift. A task that pushes Webb's sensitivity to genuinely remarkable extremes, given how faint an object at this distance actually appears from Earth. Webb accomplishes this partly through its enormous 6.5 meter primary mirror, more than 2.5 times the light collecting area of Hubble's mirror, and partly through its position nearly 1 million miles from Earth, shielded from the sun's heat by a tennis court-sized sunshield that keeps its instruments cold enough to detect the faintest possible infrared signals without being overwhelmed by the telescope's own thermal glow. And this story is very likely far from finished. The research team's own published conclusion, included directly in their paper, reads almost like a preview of what's still to come. They wrote that Webb itself appears poised to drive a series of great expansions of the cosmic frontier, and that previously unimaginable redshifts, approaching the era of the very first stars ever to form in the universe, no longer seem far away. That's not idle speculation. It's a direct assessment from the team that just broke the record, suggesting they fully expect this specific record to be broken again, potentially soon, as Webb continues its ongoing survey work. Compounding that expectation, astronomers are also looking ahead to the Nancy Grace Roman Space Telescope, a new infrared observatory specifically designed to survey enormous swaths of the sky at once, potentially as soon as late 2026, which researchers expect will help identify considerably more candidate early universe galaxies for follow-up spectroscopic confirmation by Webb, dramatically expanding the pool of extremely distant objects available for study beyond what any single survey using Webb alone could realistically achieve. So here's where this genuinely leaves us. A galaxy smaller than almost anything in our own cosmic neighborhood, sitting at a point in time just 280 million years after the birth of the universe itself, already carrying as much mass as a small galaxy currently orbiting our own Milky Way, already caught mid-burst forming new stars at a startling rate, and already displaying a specific chemical signature scientists associate with some of the oldest stellar structures known to exist. Every part of that description runs directly against the standard, carefully constructed timeline for how galaxies were supposed to form and mature in the earliest chapters of cosmic history. And the scientists who found it aren't hiding from that tension or trying to force the data into a comfortable, pre-existing narrative. They're publishing it plainly, in their own words, as something that looks nothing like what anyone predicted, then getting back to work trying to figure out why. If genuinely rethink everything discoveries like this, the kind actively reshaping an entire field of science in real time, rather than simply confirming what researchers already expected to find, are exactly what you come here for. Subscribe and turn on notifications, because between MOEM Z14, JWST Z13-0, and whatever record Webb inevitably breaks next, the story of exactly how our universe's very first galaxies actually came to exist is still being written, and we'll be here to bring you every new chapter the moment it's confirmed.